Hello to all of you. Now we will discuss the selected DC network problems, and we are already on our problem solving, and the problems again will be uploaded on the description page of this video in my YouTube channel. Okay, let us have the practical applications. Problem number 1. So this problem number 1 is you need to solve the last problem number 1 in lesson at lesson 1.3 using voltage divider principle. Now this is the shortcut method to solve this problem. As you can recall, that problem we have 115 terminal voltage here, DC voltage, and resistances you have 4, 12.4, 8.6, and 14.7 and 16.2 respectively. We need to get what is voltage V2. Now this is the Chipips method to solve this problem. Okay, so the most practical one is using a voltage divider principle. Now using voltage divider principle, V2 is equal to total voltage V and times multiplied by resistance 2, then all over the total resistance. Then substituting all of the values, 115, 8.6 over the total resistances, that is 12.4 plus 8.6 plus 14.7 plus 16.2, it will yield with an answer of 19.06 volts. So again, Chipips kapatid. Now we will discuss our next problem, which is problem number 2. So we need to read this problem here. A 10 ohm and a 20 ohm resistance are connected in parallel, and another resistance which is in 5 ohms is connected in series with the two. If the supply voltage is 48 volts, what is the current that is flowing at the 10 ohm resistance? Okay, to solve this problem, we need to have the circuit first. You have a 10 and a 20 here, which is in parallel in series with 5 ohms, and they are connected across the 48 volt DC source. Our main goal here is to get this current I1. Okay, the question is, how can we get that current I1? The methodology here is much practical. Is we need to get IT first and then use current divider principle. So by using current divider principle, but you need to get first the total current. So RT is 10 in parallel with 20 plus 5. We already described this one during our resistance combinations. And then product all over the sum, 10 times 20 over 10 plus 20. And then you add 5. Now if we compute this one, the answer is 11.67. Then by Ohm's law, total voltage over total resistance, 48 over 11.67 is 4.113. Now, to get the current I1 here, or the current at the 10 ohm resistor, by using current divider principle, you need to have the total current here, which is 4.113. Then get the adjacent resistance, and then R adjacent plus whatever your resistance at your current 1. So in this case, R adjacent is 20, then all over 20, R adjacent plus 10. Okay, if you simplify this one, we have a current here of 2.74 amperes. Hi, now we will continue our problem solving on selected DC network problems. So problem number 3, so I will read the problem first. There are two batteries with an EMF of 12 volt and 11.8 have internal resistances of 0.15 and 0.12 respectively. The two batteries are now connected in parallel, supplying a common load of 2.5 ohms. We need to find the load current in amperes. So to solve the problem, we need to draw the circuit first. So the circuit here are parallel branches of two batteries, wherein the battery have its internal resistance of 0.15 and 0.12 respectively. Then the batteries have a rating of 12 and 11.8 respectively. So they are supplying a common load of load of 2.5 ohms. So our main goal is to get the current at the load side, but before you do that, you need to get the terminal voltage V, and by Ohm's law, we can now get the current. The most practical solution here is by using the Millman's theorem that we have already described or discussed from the previous slides. So by using Millman's theorem, we can solve the terminal voltage V here. So as I recall, what is Millman's theorem? States that the load terminal voltage here can be computed by the summation of all of the short circuit currents divided by the summation of all of the conductances. Now, if this is in DC, that is conductance, but if that is in terms of AC, alternating current, these conductances will become admittances. So hence, to solve the problem, the short circuit currents here is this current here at on this branch, which is 12 all over 0.15, and then the short circuit current as well here at the second branch, 11.8 over 0.12. Now this one is 0 simply because there is no battery source. So that is 0 over 2.5, automatically that is 0. And then you divide it by 1 all over 15, plus 1 all over 0.12, and then plus 1 over 2.5. By using your calculators, the answer is 11.58. And by using Ohm's law, V all over the total resistance R here, which is 11.58 over 2.5. The answer for this problem is 4.63 amperes. Hello to all of you. Now we will discuss a much interesting problem here that applies TEC, NEC, and the maximum power transfer MPT. Okay, let us read the problem first. Two DC sources connected in parallel, having a 120 volt and 199 volt respectively. Their internal resistances are 3 ohms and 2 ohms. So they supply a load with an unknown resistance R, which is this one, through a total feeder resistance of 0.8 ohms. We need to find the Norton equivalent circuit, or NEC, of the parallel sources only. Actually, this load here, okay, which has an arrow sign, is connected at points A and B. However, our main goal is to get the NEC of the parallel sources only. So you need to get the Norton's equivalent of that, and then after you already obtained the NEC, you need to connect this circuit here at points A and B, as what we have done on the basic fundamentals. Now we need to concentrate at this parallel sources only and get the total, or determine the equivalent circuit at Norton's of this combination. Okay, first, much practical way to get the short circuit, the Norton current, is to transform this series combination to a current source and a resistor, which is your constant R. So what I have done here is just Ohm's law, no? To get the current, you need to divide the voltage by the corresponding resistance, or transforming this series combination to a parallel combination of a current source and your resistor. So what will happen here is 120 you divided by 3, the answer is 40 amps. 119 all over 2 ohms, the answer is 59.5 amperes. And then the resistor that is in series here is the same with the parallel resistor at the transformation. So that if this is 3 connected in parallel. Now you will do the same pattern here at the 119 volt here and the 2 ohms. So the answer is 59.5, and then you have 2 ohms. And the points A and B here is these points. And then, as we have mentioned on the basic fundamental, to get the Norton current, you need to short the terminals and get that current there, IN. Okay, now, to solve that current IN, we have two nodes here, A and B. have KCL at points A. By the way, I forgot to mention, how did we arrive with this direction here, an upward direction? You can see I have the terminals plus minus here, the polarity marks. As we have mentioned before, that is voltage rise, assume as voltage rise. So you have your currents I1 and I2 respectively here. So you expect it will become an upward current source. Okay. Now KCL at node A, so we know KCL, current entering is equal to current leaving. Current entering at node A, which is 40 amperes and 59.5, is equal to the current leaving IN. And if you add this one, the answer is 99.5 amperes. Now, to get the Thevenin's resistance RN, so we have described this one from the TEC and also at NEC, that if you have a current source, you need to zero the independent sources here. So now you have a current source, so you need to open. So we open this one so that the current has become zero. And then you have 3 and 2 here, and get the total resistance at points A and B. Now it's very clear that 3 is in parallel with 2. Therefore, 3 times 2 over 5, 3 plus 2 is 5, is equal to 1.2 ohms. And hence, our final answer here for the Norton's equivalent circuit is a 99.5 IN and 1.2 ohm resistor in parallel. And this is the points terminal A and B. And this is the equivalent circuit of the parallel sources there. Now we will apply this one on maximum power transfer on the next problem. Hi, now we will discuss our last problem here, which is problem number 5. Okay, this is problem number 5. So let us read the problem first. Referring to the last problem is problem number 4. Find the value of R so that maximum power is transferred to it. Okay, as we have discussed on maximum power transfer, it's more practical that we need to get first the Thevenin's equivalent circuit. Let's have our last problem from the last slide, that we have the NEC here. Okay, you have the 59.5 amperes in parallel with 1.2 ohm. Okay, and you have terminals A and B. Now, this is the equivalent of the parallel sources. Now you can transform it to its corresponding TEC. Initially, okay, I will not connect this one. Okay, initially, this is the Thevenin's equivalent, 1194 volts and 1.2 in series. Now, how I arrive on a 1194 answer? What I've done is I just multiply the 59.5 by 1.2 here, because as we have recalled here, that the Norton's current is simply equal to Thevenin's voltage all over RTH. Okay, so to get the Thevenin's voltage here, multiplied IN by RTH, or your resistance here, which is 1.2, which is RN is equal to RTH as well. Now, just multiply this one, and it will yield with 119.4, which is in series with 1.2. Now, the problem needs maximum power transfer. So, as you can recall from the last slide, okay, we did not connect points A and B here from RF and R. The RF here is the total resistance. Please take note, this is already total resistance. But if that is not total resistance, you need to multiply it by 2. But the problem states that 0.8 ohms is total feeder resistance. And please take note as well, to get the total feeder resistance is always twice of the resistance of one way and then another way, so two-way. Okay, so here we already have total resistance, so you do not need to multiply by 2. Okay, now we need to connect those points there with the RF feed resistance and the R, which is your load. So assuming that is your load, become maximum is a variable load, we already described on maximum power transfer that the load resistance RL is equal to RTH. And thus, what I will do here is, I have points A and B, A prime and B prime here, and we need to get the Thevenin's resistance RTH prime at points A prime and B prime. So you need to isolate, you need to disconnect that resistance and get the total resistance RTH from point A prime and B prime from the load. So hence, you have 0.8 plus 0.2, which yields to a 2 ohms answer. So this is a practical problem because you already applied TEC, NEC, and NPT in one problem. Okay, thank you very much. So we already done with the DC network theorems. Our next goal or next topic will be DC transients. Hope to see you there, and don't forget to subscribe to those who are new on my channel. Maraming salamat po.